one of the very interesting distributions is called a log normal distribution. So let me first define the distribution for you, and then we'll go and see what the applications of log normal distribution are. By the way, log normal distribution occurs a lot in the real world, surprisingly. So what it says is your random variable x is considered to be log normal, is defined to be log normal if log of x, the natural logarithm of x, is normally distributed. Is normally distributed. Okay, just like normal distribution, log normal also has two parameters which are mu and sigma. Okay, so a random variable x is said to be log normal if log of x, this is by the way natural logarithm. So this is natural logarithm, often written as ln. Okay, so here is the definition that I just told you. Okay, so if the variable x is log normally distributed, then y, which is log of x, this is natural logarithm of x, has a normal distribution. Okay, and this is how it looks. Now let's look at the shapes here. Okay, so first thing that you should notice, this is your PDF. By the way, this is a continuous random variable. Okay, so let's take your red curve here. It has a mu of 0 and a small variance or a small standard deviation. As this is also mu of 0 and with a standard deviation of 0.5. This is again all these three curves, the red, blue, and the green curves have the same mu of 0, but the standard deviations are changing. Okay, so one thing that you should notice is this red curve looks somewhat like a Gaussian curve, but it's not truly a Gaussian curve, because if you see this side, it falls off very quickly, while on this side, on the right side, it starts falling much slower. Okay, and as sigma increases, as your standard deviation increases, the fall, see, compare your red, green, and blue. Okay, your red curve has a standard deviation of 0.25. Your green curve has a standard deviation of 0.5. Your blue curve has a standard deviation of 1. So as standard deviation is increasing, the PDFs tends to have a fatter tail. Okay, they're going to get more and more skewed, if you want to look at it like that, right? They're going to get more and more skewed, right? And they're going to have a fatter and fatter tail. This occurs a lot in nature, by the way. Okay, so the simplest way for you to understand, and of course the CDFs also look, the CDFs can be easily interpreted from PDFs. Okay, you can obviously compute CDF from PDF, right? Now here is, so one thing that you should notice is the PDF form looks very much like a Gaussian distribution, except for the log term here. Okay, it looks very much like a Gaussian distribution, very much like it, except for this term here. Okay, again, the mean and median, you can, of course, we are not very worried about it, but the shape of log normal distribution is itself very important. Now let's go and figure out some very interesting applications. So in Wikipedia, for almost all distributions, you'll come across this occurrence and applications. This is super important. So again, by the way, I've come across a lot of log normal distribution in my personal career because I've worked at internet companies. The length of comments posted on an internet discussion forum follow a log normal distribution. So a log normal distribution, to put it bluntly for you, looks like this, right? Right? So it has a skew. It has a skew like this. Oh, by the way, I just wanted to show you the skew part of it. I completely forgot. Sorry. I wanted to show you the skew part, right? Its skew is very different, right? So let me show you the skew part of it. Where is skewness? Its skew is not zero like uniform distribution, by the way. Okay, so let's go to applications. Sorry to go back and forth, but I couldn't stop myself from doing that. Okay, let's go to occurrences. Okay, so this is a very interesting thing. So if you take a log normal distribution that is like this, right? This is how a log, so this is your random variable x and this is its PDF, right? It's its probability value. So what it says is lot of comments are actually short, but there are a small set of comments which are actually very long. Okay, this is what it means. The length of comments posted on internet discussions, most of them like Quora, right? Internet discussion forums could be your Reddit, it could be Quora, all these things. So what happens is most of your comments are small. A lot of your comments are small, but there are a small number of comments which are very, very long. Similarly, the user's dwell times on online articles. Dwell time is basically time spent on a page or on an article, follows a log normal distribution, because most people spend very little time on an article, but there are a small set of users who spend a lot of time reading the article, analyzing the article, and probably posting comments on the article, right? So for human behaviors and for especially on the internet, you'll observe a lot of log normal distribution. You'll observe a lot of log normal distribution on the internet, a lot of it. There is a related distribution called Pareto distribution that we'll discuss later in this section, which also occur a lot on the internet. And since I've worked at internet companies like Amazon and Yahoo mostly, I have come across log normal a lot in my professional career. Having said that, let's go and see some other very interesting. So, by the way, the other interesting thing is incomes in economics. In economics, there is good evidence that for 99, almost 97 to 99% of people of your population, their incomes are log normally distributed. But the distribution of the top 1% of the higher income individuals follows something called a Pareto distribution. We'll come to what it is. Okay. Again, log normal occurs a lot in finance and economics. So in finance, there's something called a Black-Scholes model, right? And in finance also, you come across heavy tail distributions. So this is called a heavy tail distribution, right? Because I have significant number of points in this tail. So this is called the tail of the distribution, right? And this is skewed distribution, as you would quickly realize. It's skewed towards one side. And in economics, what happens is incomes of almost almost 97 to 99% of people follows log normal distribution. Except, so if you take the top 1%ers or top 2%ers of income, most income is log normally distributed, which means most people make very little amount, and there are some people who make millions of dollars of income. Okay, so this occurs again a lot in finance and economics for you. Now we have seen the PDF and CDF of log normal distribution. Now comes an interesting question that I wanted to go over. Imagine if somebody gives you a random variable x and they tell you that it is a log normal distribution with a mean of mu and a variance of sigma. Okay, now the question for you is, how do you see, because lot of techniques, lot of analysis, okay, lot of algorithms both in machine learning and otherwise have been designed for normal distribution. If something is normally distributed or Gaussian distributed, it's very easy to analyze the data because a lot of algorithms are built and a lot of analysis. If you recall, your two standard deviation of 95%, your 67, 95, 99.7 rules, all of them we know almost by heart for Gaussian, but not for other distributions. So as soon as I know that x is a random variable which is log normal, I can define y, which is log of x, which is natural logarithm, of course. Natural logarithm is base e. Okay, I can compute the natural logarithm of x, or which this is often written as ln of x, as we saw earlier. They both are similar. They both are exactly the same, by the way. Okay, and now I know that y is normally distributed with a mean and variance. Right? As soon as I know this, so whenever you're given a random variable which you know is log normally distributed, one of the first things you can do is you can convert into Gaussian distribution, and from Gaussian distribution you have all the beautiful theory, all the beautiful mathematics, and all the beautiful interpretation of a Gaussian distribution that you can use. Now the next question that I have for you is, how do you determine? So imagine if you're given a random variable x, which somebody tells you that it is log normally distributed with mu and sigma, right? How do you test this? How are you sure that x is normally distributed? This is what you think. Suppose you're given values x1, x2, x3, so on and so forth, xn. You're given n values. Now the question is x log normally distributed? Okay, how do you determine that? So it's very, very simple. For each of these values, you take log of x1, natural logarithm, you take of log of x2, so on and so forth, you take natural logarithm of xn. Okay, let's call each of them y1, y2, so on and so forth, yn. Right? Now, given y1, y2, yn, we already learned about QQ plot. Right? We just learned in the previous section about QQ plot. You can employ QQ plot to determine if yi's are Gaussian. We can employ QQ plot to answer the question if yi's are Gaussian. If yi's are Gaussian, then immediately we can declare if this is true, then your x is also log normal. It's such an easy thing. Okay, log normal, by the way, occurs a lot in nature, and it's extremely easy to test whether a distribution is log normal or not by just taking the logarithm of the values of the distribution that you have, or the observations from the distribution that you have. You basically compute log, and you use your QQ plot to very easily test whether your yi's are Gaussian. And if your yi's are Gaussian, which are nothing but log of xi's, then your x is log normal by definition. Right? So this is a very, very simple technique for you to determine whether a given random variable is log normal or not. By the way, if you ever work at internet companies, if you ever work at internet companies like Amazon, Google, or even small startups, you will encounter log normal distributions and Pareto distributions a lot. Trust me. So you'll see plots like this whenever you plot the PDF of anything. More often than not, you'll find distributions like this, and seldom you'll find your beautiful Gaussian distributions. This happens few times. This happens fewer times, and this happens many times. If you're working in internet companies, or wherever human behavior, or if you're working in finance or economics and things like that. So whenever you see a distribution like this, it could very likely be log normal or a Pareto distribution. And we'll learn more about Pareto distribution little later in this section.